Okay, let's get started with section 12.8, the last section in chapter 12. So we'll finish things up with linear programming, which is an extension of 12.7, the systems of linear inequalities. So just to review here, last class we talked about linear systems of inequalities. We had this problem here, and so in this one remember that x plus y was less than or equal to 30,000, x was at least 20,000, so greater than or equal to 20. Y was less than or equal to 5. And so in this, all we did was graph it. What we're going to extend now is to figure out how to maximize it. So if we're the financial advisor here, we're going to make some recommendations, and then based on our recommendations, we're going to say, hey, if you do it this way, you're going to maximize your money, or you're going to minimize your money, depending on what type of problem it is. All right, so that's the extension for 12.8. How do we take a system of linear inequalities, something like this that we did last time, right, and figure out where's the best place to be within those restraints? All right, so we're going to introduce your maximize or minimizing function. It's called the objective function. The objective function, z, okay, it could be another letter, but equals some function that we're not going to graph. What we're going to do is we're going to take numbers from our graph and plug it in to this to figure out the best place to be. All right, so certain conditions that will either maximize or minimize your situation. Let's take a look at an example and see if we can make some more sense out of that. So let's consider this linear programming problem. We're going to maximize I equals 0.005x plus 0.0008y. All right, this is the thing we're not going to graph. Don't graph that. We're going to take our graph and plug it back into that at the end. So let's go ahead and graph here. And so 5, 10, 15, 20, 25, 30, 35. And we're going to go, same thing, 5, 10, 15, 20, 25, 30. We'll go one more to 35. All right. These two are saying we're in the first quadrant, so we're already good there. X plus y is less than 30, so using intercepts, we can connect those. And we're going to be below that. X is greater than 20. Okay, so x is greater than, we're going to be on this side here, and y is less than 5. All right, we want to be below this one, all right, and below that other line, so it looks like our perfect region here is going to be right in here. All right, so now we need to say, all right, what would maximize this equation up here? The points that are going to maximize this are going to exist at one of the 4 edges of our feasible region. All right, the green part is called the feasible region. So we're going to figure out what those coordinates are. So this one down here is fairly straightforward. That's 20, 0. This one here is straightforward. That's 30, 0. All right, this one here is not too bad. This is 20, 5. And it's the last one that's going to give us a little bit of trouble. That's where this line is matching up with this line, right? So that's when y is 5. So if y becomes 5, x plus 5 equals 30. So that means that x needs to be 25 there. So not too bad to figure out that point. So this is going to be 25, 5. All right, which of those is going to maximize our constraint up at the top? All right, so we say I equals 0.05x plus 0.08y, and we just need to plug them in. All right, so we could plug this in a couple times if we wanted to, or we can use our calculator. I'm going to do it by hand first, and I think I'll walk us through how to do it on the calculator in class, just for some time saving here. So I equals 0.05, let's plug in 25, plus 0.085. All right, and the other one would be I equals 0.0520 for the x plus 0.085. And we can tell right away that this is going to be more than this because these numbers are the same. This number is smaller. Let's get rid of that. All right, and it's the same thing. 20, 0, 30, 0 are going to be smaller as well. So it's this point, 25, 5, that maximizes our linear programming problem. All right, a lot going on there. There's only a couple examples here, but each example is a little bit lengthy. So let's take a look at what we did here. A solution to a linear programming problem consists of a feasible point that maximizes or minimizes the objective function. All right, so these were our feasible points, the 4 dots here. This is our objective function, and in this case, we're trying to maximize it. All right. Location of the solution of a linear programming problem will always occur at a corner of the graph, a corner point of the graph of the feasible points. All right. If there's multiple solutions, at least one will happen at the corner. All right. This is if your answer could be a greater than or a less than. You're still looking at the corners. All right. The corresponding value of the objective function is unique. That means that when we plugged in our numbers for this point or this point or this point or this point, we got different values. All right, let's look at the steps here. If these are tricky for you, you might want to have these in your notes step by step. You could pause this video and write it down. But this is just step by step what I did in the last problem to get all of the values. All right, so let's try one more, 2 more here, and then you'll try some problems on your own. So minimize this expression subject to these constraints. All right, so it looks like the biggest x I've got is 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the biggest y I'm going to have is 7. 1, 2, 3, 4, 5, 6, 7. So I'm less than 7. There's 7. I'm less than 10. I am hitting intercepts at 5 and 5 from this equation. And I'm in quadrant 1. That's what those are saying. All right, so I need to be greater than this diagonal line. I need to be less than the x. And I need to be less than the y. So here's our feasible region. Draw that out there. All right, so somewhere in here. And so we have 4 feasible points. 1, 2, 3, 4. Oh, sorry, 5 feasible points there. Let's list them out. This is 10, 0. This is 5, 0. This is 0, 5. This is 0, 7. And this point here is 10, 7. And we're going to minimize this expression. All right, so pretty good guess that it's going to be one of these because it's the smallest value. So let's go back to our objective function. Z equals 3 times, let's try this equation first. 0 plus 4 times 5, that's 20. Let's check this equation. And here, z equals 3 times 5. This is going to be smaller. 4 times 0, that's 15. All right, and is there any way that you can get smaller than that? 7 times 4 would be more. 10 times 3 would be more. So 5, 0 will minimize our objective function. All right, 5 and 11 are yours to try. Okay, last one. A factory manufacturer manufactures 2 kinds of ice skates, racing and figure skates. The racing skate requires 8 work hours in the fabrication department, whereas the figure skate requires 4 work hours. Each of them require 2 work hours in the finishing department. The fabricating department has available at most 224 work hours per day, and the finishing department has no more than 72 work hours per day. A lot of information. We're going to have to sort this out. If the profit on each racing skate is 15 and the profit on each figure skate is 12, how many of each should be manufactured each day to maximize profit? Okay, so profit is what we're trying to maximize. So let's start with our objective function. That's going to be the money. So we want to maximize profit. So I'll use P. P equals 15 racing. So let's make racing X plus 12 for your figure skating. Okay? Figure skatings are going to be Y. So that's your objective function. That's not what we're going to graph. We know we're going to be in quadrant 1 because you can't make negative ice skates. All right, so now let's figure out how we can come up with a couple more equations. All right, so the racing skates require 8 work hours in the fabrication department. So the fabrication, so let's say 8x plus 4 for the figure skating there. And the fabrication department has 224 work hours per day. So if you add those together, you got to be less than or equal to 224. All right? And the finishing department, and remember that was 2x and 2y, both of them required 2 hours in the finishing department, has to be less than or equal to 72. All right? So there we have 2 linear equations, and we can set this up. Linear inequality, sorry. All right, so let's find some intercepts here. In this one, 224 divided by 8. Let's grab the calculator. And actually, you know what? Let's finish this off using the calculator so we can do this. All right, so we know that, clear that out, we know that y is going to be equal to negative, let me put this in parentheses, negative 8x plus 224 over 4. That's our first equation. And our second one here is going to be negative 2x plus 72 over 2. All right, and let's go give ourselves a good window here. How about negative 5, just so we can see the axis, to how about 100? And we can count by 5, so we don't have to have a whole bunch of tick marks there. And how about negative 5 to 100 also? We might zoom in from that. But let's see what we got here. All right, there's one equation. And there's another equation. Oh, nice. All right, let's do a box zoom here so we can get a little closer in. Okay, and since we know that we have to be less than both of these, it's going to be the shaded region down here. So I'm going to redraw this just on our graph here. This over a little bit. So we've got a graph that's looking like this. Right? And our shaded region is underneath it here. All right, so what are the feasible points? I've got 1, 2, 3, 4. And so we need to figure out what all of those are. Okay? And if we're going to maximize profit, our best bet is it's going to be over here. It actually is. I want to walk you through the steps of finding that point. That's the point where these two lines intersect. So let's go back here and find the intersection. Calculate our intersection from curve 1 and curve 2. And what's our best guess? Oh, there's pretty good. It intersects at 20, 16. All right, so we could plug 20 and 16 into our maximization formula, and it would work out. Okay, we can walk through all the steps there. I think I want to have you spend more time on 19 walking through this. So go ahead and try 19. If you still have questions, we will go over that tomorrow in class. All right, good luck with the rest of the problems that you haven't solved so far.